All right. So the first thing I'm going to do here is, unlike some of the previous easier problems that we did, I don't know the values of the reactions right off the top of my head. So I'm going to do that part first. So I'm going to come over here to the right and draw a free body diagram and put the loads on. 600 pounds, an applied force, and then there's also an applied couple of 4,000 pound-feet. And I'll go ahead and put the dimensions in: 10, 5 feet, 5 feet. And then on the left side, I'm going to assume positive shear at A. And on the left, I'm sorry, I said left, that's right, left. On the right-hand side, I'm going to assume positive shear at B. And I don't have any moments here because these are pin and roller connections, moments here. So now I'm going to use my equations of equilibrium and try to find these shear values. So I'm going to sum moments using right-hand rule for my sign convention, and I'm going to sum moments about A and make sure it's 0. So there's my equilibrium statement. So let's do it for this beam. So starting about A, this 600-pound force creates what kind of moment about A? Positive or negative with right-hand rule? Negative. So the force is 600 pounds, and the moment arm is 10 feet. I'll come back and do this moment in a minute, but let's go all the way over here to my shear force at B. What kind of moment does that create about A? Positive or negative? Also negative. Shear at B. And that has a moment arm of 20 feet. And I am summing moments about A, so I have to worry about this applied moment. I'm using right-hand rule, so this is what kind of moment? Positive.
Would it be negative though?
No. It's an applied moment, right-hand rule, right-hand rule.
Drawing.
Oh, I drew it backwards. I'm working a different problem, I guess. Let's change it. Let's make it the same problem. Thank you. You guys are smart. So that would then make this negative. So from that, I should be able to solve for the shear at B. I don't know what that is. 6,000, 10,000, 500?
Yeah.
Negative, right. And then we can sum forces in the y direction. I'll assume up is positive. That's my equilibrium. And doing that, the shear force is up, so that's a positive force. This shear force is down, so that's negative. And the 600 pounds is down, so that's negative. And then, of course, we're going to put our value for shear force at B in there. And when you solve for the shear at A, you get, 100. Is that right?
Yeah.
-5. So I'll just kind of put a little line there to block that off, and now we'll take that information over here and draw shear force and bending moment. So I'm going to first create a little template. There's my start, and there's my end. Now from our previous work, we know that something's going to happen in the shear diagram as I go from the left side to the right side of this force. So that's a pretty important point. So I'll add that to my template. And you might remember from our discussion in class that when you have a concentrated load like this, concentrated couple, a moment, that the moment diagram is going to make an instantaneous jump. So I'm going to add that part to my template also. So that given, I'm going to go ahead and define positive x, positive shear. All my shear values are going to have units of pounds. And now I've got kind of my template set up. Now I'm going to apply the information that I have about shear and how it changes to construct the diagram. So starting here at A, do I know what the shear at A is? Yeah, we found it. It was equal to 100. What was the shear at B? Did we find that? Yeah, it was negative 500. So I have a beginning and an end. Now, I'm going to have to write this down here because I didn't leave myself much space, but remember, the change in shear is the area under the load curve, and the slope of the shear diagram is equal to the load. So looking at the loading, I'm going to break it up into two segments, one that goes from about 0 to 10, and then we'll worry about how we go from left to right here. And then on the right-hand side, looking at forces, which are shear forces, I'm going to look at the change over this period. Oops, I'll do that again. So let's do the first 10 feet. So the change in shear between A and 10 feet should be what? The area of the load curve. And the area of the load curve from 0 to 10 is 0. No change. The slope of that curve is given by the load, and the load is 0. So 0 slope, horizontal line. So it looks like I got constant shear over the first 10 feet. Now as I go from left to right, how much does the shear change? Remember, the change in shear is equal to the load, which in this case would be minus 600. So 100 minus 600 is minus 500. Now the change in shear just to the right of the load to the point B, that change in shear is given by the area of the load curve. And what's the load from just to the right of the load to B? It is 0. So there's no change. So good. Minus 500 plus 0 is still 500. Yay. It works. And then, of course, the shape of the shear diagram is given by the load. And we know the load value there is 0. So 0 slope. And there's your shear diagram. So if you made any kind of connection in your structure, on the left side, you have to worry about a shear of 100 pounds. On the right-hand side, you have to worry about a shear of 5 times as much, 500 pounds. Okay, so let's, now that we have a shear diagram that looks pretty decent, let's draw a moment diagram. So again, we'll assume positive x, positive value for moment, and all these units will be in pound feet. What do we know about the moment here at the starting point on the left side at A? It is 0. What about on the end? Do we know something about the moment here at B? It is 0. We also know that the change in moment between any two parts on the load diagram is the area under the shear. And that the slope of the moment diagram is the value of the shear. You can see our shear diagram is in two parts. One over the first 10 feet and then one over the second 10 feet. But in addition to that, we've got this applied moment. So really, we're going to end up breaking our shear diagram up into 3 parts to deal with. And I'll just put more hatching in this one to show you. We're going to deal with this change and then this change. And as we go from left to right here at 15 feet, we'll have to handle that change in the moment, and then we'll come back and finish it off with this piece, this last 5 feet. So starting with the first 10 feet, the change in moments, area of the shear diagram. What's the area of the shear diagram here? Yeah, it's a rectangle, base 10 times height 10, that's 1,000. So 0 plus 1,000 is 1,000, right? And the slope of the moment diagram is the shear, and the shear value is constant and positive. So again, if we looked at this, we would see that it would go up 100 feet for every foot it goes across. So there's that part of my moment diagram. Now over the next 5 feet, this double hatched area here, the change in moment is the area of that part of the curve. What's the area of this part of the curve? Well, it's a rectangle again, so the base is 5, the height is minus 500. So that's negative 2,500. So 1,000 minus 2,500 is negative 1,500. And what is the slope of the moment diagram? Well, it's given by the shear value. And the shear value from here to here is constant and negative. So there's a constant negative slope. Now, as I go from the left side to the right side and I pass underneath the applied moment, the moment diagram is going to jump 4,000. Okay? If you have a clockwise moment, the jump is positive. So negative 1,500 plus I'll say it right in a second. 4,000 is what? Positive 2,500. So now I'm here at positive 2,500 just to the right of the applied moment. So the change in moment here should again be the area of the shear diagram. What's this part of the area of the shear diagram here? It's also base times height. 5 times minus 500, that's negative 2,500, and that brings us back to 0. Yeah. And then what's the slope? What's given by the shear, and the shear again is constant and negative. Looks like that. So there's my moment diagram. So what is the maximum moment in this beam? 2,500, and it occurs where? Just to the right of the applied couple. What's the maximum negative bending moment? And negative 1,500, and it applies just to the left of the couple. Do I really care where the moment is 0 right here? Right now, I do not. We only really care about where the shear goes to 0. And the shear is 0 somewhere in here, right? As it goes from 100 to minus 500. And you'll notice that if you follow down here, hey, look, there's kind of a maximum value. It's a local maximum. It's not a global maximum, but it is a maximum value. Any questions about this one? Well, let's work another one then. How many more? I don't know. How much time do we have?